The topic of this first lecture is convex hull. Let's start with an example of an application where we may need a convex hull. Let's say that you work with a group of biologists who study certain animals, for example, black rhinos. And these biologists would like to know the area of habitat of these animals and the extension of this habitat. To the first approximation, this habitat can be described with the convex hull of all the locations where black rhinos were observed. For example, on the left-hand side, you can see that they have been spotted all over Africa, and the shaded region is the smallest convex area that covers all those locations. So as an algorithm developer, you may suggest to your colleagues to use the convex hull of all these sightings as an approximation for the area of the habitat. So now let's formally introduce the notion of convexity and of the convex hull. We say that a shape, a geometric shape, is convex if for any 2 points in it, the line segment connecting those 2 points completely lies in this shape. Let's do a quick test of understanding. Please think about the following geometric objects and answer the following question. Which of these objects are convex and which are not? So take a moment to think about it and fill out the answers. Okay, so now we are ready to define a convex hull. For any region in the plane or for any subset of the plane, its convex hull is defined as the smallest convex set that contains that subset. So here on the bottom you have 3 examples. The bottom left is depicting the convex hull of a set of points. In the middle, a chain of segments, and on the right, a convex hull of a simple polygon. In all these cases, you can see that a convex hull is indeed the smallest convex set that completely contains the given region or a set of points. Another analogy that sometimes is convenient to use or to visualize what a convex hull is imagine that a set of points given in the plane is a set of nails that you nail in a wooden plank. And now we surround all these nails with a rubber band and release the rubber band. So the shape that this rubber band will take while it's retracting is the smallest convex set and is the convex hull. Now that we have defined what a convex hull is, we can formulate the convex hull problem. The problem is asking us to give an algorithm that computes the convex hull of a given set of endpoints. And we want to compute it as fast as possible. So in the following few videos, we will discuss these problems and multiple different solutions to this problem. First, let's discuss what we can expect from an algorithm solving this problem. So we know that the input has endpoints and is represented with 2 end coordinates. So the input has linear size. So what can we say then about the output to this problem? If we assume that the input endpoints are distinct, and it is a safe assumption to make, then we can say that the output will have at least 2 points. If all the points somehow fall on one line, then the convex hull will be described by 2 endpoints, right? And at most, the output can have endpoints if all endpoints lie in the convex position. Okay, so then what it means is that the output of the convex hull problem requires between a constant and a linear size space to describe the solution. Okay, so let's think about the following question. Can we hope to design an algorithm that will compute a convex hull of endpoints faster than in linear time in the worst case? So let's take a second to think about this question. Okay, to answer this question, we should think about the representation of the output. What is the convex hull? It is a set. And how can we represent it? Well, the figure on the right-hand side gives us intuition that the convex hull will be a simple polygon, and thus we can represent it as a sequence of vertices. We have already said that in the worst case scenario, all endpoints can lie on the convex hull. So the polygon representing the convex hull will require linear space to be described. And thus, if we are relying on an algorithm that will report the convex hull to us, it will have to spend at least linear time to report the solution. So the output is a convex polygon. It should be returned as a sorted sequence of points along the boundary, and the usual convention is that we are going to return them in a counterclockwise order along the boundary. Okay, now that we know that the linear time is the minimum that the algorithm can take, can we actually hope to find one? The answer to this question is not that straightforward, and we will discuss it in the first session. Before we get to designing the algorithms for the convex hull problem, let's discuss what steps we need to take to develop an algorithm in general. When you are given a new geometric problem to design an algorithm for, we suggest that you start by drawing many different sketches to gain insight into the problem, make various observations, find useful properties based on which you can develop the algorithm. So let's see an example of how this process would work. So for the convex hull algorithm, we want to draw a lot of sketches, gain insight, make observations, and find properties that will be useful when we will be developing algorithms. So what can we say after drawing many sketches of convex hulls? What properties a convex hull may have? Well, firstly, we have already mentioned this, but let's repeat this and state it as a property that a convex hull of a set of points will always be described by a subset of points, and the edges of the convex hull will be the segments connecting a pair of points lying on the convex hull. Finally, if we draw a line containing an edge of a convex hull, in the example, this is the line going through 2 points P and Q lying on the convex hull, we can make an observation that all the remaining points lie to the left of this line if the direction of the line points in the counterclockwise direction around the boundary of the convex hull. So we are going to formulate this as a property. The supporting line of any convex hull edge has all input points to one side. And now making these observations and stating them as properties will allow us to suggest several different algorithms to find convex hulls. As a first approach, let's start with a very simple and straightforward algorithm that uses the last property that we have formulated to find all the edges that are the edges of the convex hull. So what the following algorithm does, it considers all ordered pairs of points P and Q. It considers a directed line going through P and Q and checks if the remaining points lie strictly to the right of the directed line. If no such point exists, then the algorithm recognizes that the edge PQ is indeed an edge of a convex hull, and it adds it to a set E. As the last step, the algorithm will take all the edges from the set E, sort them, and output the edges of the convex hull in an order counterclockwise around the points. Okay, as the first step, this is a simple algorithm that will produce a desired convex hull. But I want to suggest that you think about the following questions, and I will leave this as an exercise before our meeting on Monday. First question is about handling degeneracies. What happens in line 5 if the point R lies on the line going through P and Q? How does the algorithm handle it, and does it handle it correctly? Question number 2 is, what is the running time of the algorithm? Finally, the last question, is this algorithm robust against rounding errors? And note that robustness in geometry is a huge issue that we will be talking later in the course about when we will be talking about engineering algorithms. Let's consider another approach and hopefully come up with a faster algorithm than our first attempt. We are going to construct the convex hull incrementally by inserting points one by one from left to right. We first will compute the upper boundary of the convex hull and then the lower boundary of the convex hull. In this way, the points on the upper boundary of the convex hull will appear in the order consistent with the x coordinates. So the main idea will be to first sort all the points on their x coordinates from left to right, and then insert these points in this order one by one and maintain the upper hull for all the points that have been inserted. We recommend to start with drawing a lot of sketches, considering many different examples, making observations. So this will be a good step towards designing an algorithm. So the first observation that we can make is when we consider the upper hull of a set of points going from left to right, every 3 consecutive points on the convex hull are making only right turns. So we are going to use this property to suggest the following algorithm. We're going to start with inserting the first 2 points in our current convex hull. We will consider the third point, and if the third point with the first 2 is making a right turn, we're going to keep the 3 points in the current convex hull. So far, on the first 3 points, we have a correct upper hull. After we insert the fourth point, we observe that the last 3 points are making a left turn. In this case, we want to remove the third point from the chain. We are left with only 3 points in the chain that are making a right turn. So far for the first 4 points, we have a correct upper hull. We are going to consider the fifth point. Again, the last 3 points on our chain are making a left turn. So we are going to remove the one but last point from this chain. And again, we're ending up with the last 3 points making a right turn. So then we're moving on to inserting the next point and the next point, and so far our chain is making right turn, so it is a proper upper hull of the first several points. Finally, when we are adding the 8th point, we see that we are making a left turn now. we need to remove the one but last point from the chain. We are still making a left point in the last 3 points on the chain, so we're gonna repeat removing the points from the chain as long as the last 3 points are making a left turn. So now we are left with the upper hull chain that is only making right turns, and after adding 2 more points to it, we are done constructing the upper hull. So we are going to write down this idea of the algorithm in the following pseudocode. We start in the line 1 by sorting all the points by their x coordinate. We're gonna put the first 2 points in a list L upper that will maintain the upper hull for the first I points. And then in the for loop, from the third point to the nth point, we will append the point pi to the list L upper, and while the last 3 points of L upper make a left turn, we are going to remove the second point from the end. At the end, this algorithm will produce a correct upper hull of a set of points. So now that we have computed the upper hull of a set of points, we can repeat the same for the lower hull, and then we will concatenate these two chains, making sure that we don't have duplicate points in them. When we're proving the correctness of an algorithm, we want to make sure that the observations we have made and the properties that we used to build our algorithm are correct. And secondly, we want to make sure that the algorithm handles those degenerate cases correctly. For example, in the case of the convex hull problem, degenerate cases may come in the form of 3 collinear points or maybe 2 points with the same x coordinate. And indeed, for the convex hull algorithm that we've just developed, we want to make sure that if we have 2 points with the same x coordinate, the algorithm will behave correctly. Either we can prove that no matter in which order we process the points, the algorithm will behave correctly, or if we notice that it may not exactly behave correctly in the way that we have designed it, then we need to modify it and fix it. And secondly, how are we dealing with 3 or more collinear points if they lie on the convex hull? Do we want to include midpoints of the edges of the convex hull into the list that we output or not? This depends, of course, on the application, and depending on the answer, we may want to adjust the algorithm accordingly. And the second step is to analyze the efficiency of the algorithm. To do that, we simply identify for each line of the pseudocode how much time it takes to execute it and how many times it gets executed overall. Recall that for constant number of constant size objects, any operations on them we assume to take constant time, and we do not worry about the constant values themselves. To answer the question of how many times each line gets executed, we will consider the loop structure and figure out how many times each line of code gets executed. Sometimes a naive bound on how many times each line gets executed will be too loose, and to get a tighter analysis of the running time of the algorithm, we will need to use some global arguments. So let's analyze the running time of the gram scan algorithm that we have just developed. Line 1 sorts the set of points P by their x coordinates and thus takes big O of n log n time. Line 2 takes a constant time because it's an operation on a constant number of constant size geometric objects. Line 4 and line 6 both as well take constant time to execute, And now we have the outer for loop that gets executed n minus 2 times, and the inner while loop that we don't know how many times it executes each time, but let's just denote it as parameter ki. So now we can put all these together, sum them up, and obtain the total running time of the BRAMScan algorithm. We can simplify the expression that we get to this format. Big O of n log n is the first term, and the second term is the sum from 3 to n of big O of 1 plus ki. So now we want to argue what values ki may take and obtain the final expression for the running time. As a first attempt, we can simply say that ki will be bounded by n from above, so ki may be at most a linear function. That is because ki is the number of points that gets removed from the chain, and there cannot be more than n points removed from the chain, right? So then if we bound each ki by a linear function, we get the total running time big O of n squared. The question now, is this analysis tight? And it does not feel this way because bounding each ki by a linear function feels a bit like a loose bound. So let's try again and use some observations and some global arguments why the running time of the algorithm is actually smaller. So let's recall what happens within one iteration of the outer loop. Here I have an intermediate state of the execution of the algorithm of the example that we considered earlier. We have just added one more point to the chain, and now we will remove all the points that make the last 3 points make a left turn. And now what we were claiming is that for the first few points, this is the correct upper boundary of the convex hull. That is, all the points to the left of this red line are processed, will never be added to the chain again, and thus will never be removed from this chain again. So the global argument that we will use is that each point can be removed from this chain only once. And this gives us an upper bound of n on the total sum of all ki's. So now, instead of bounding each ki separately by n from above, we can bound the total sum of them by n from above. And we will get, as a result, the total running time of big O of n log n. So now let me summarize our intermediate result as the convex hull of a set of points in the plane can be computed in big O of n log n time. And I will also add this is the worst case optimal. We have not discussed why this is the worst case optimal, but let's discuss it on Monday in our meeting. Of course, the question that we always ask, can we do better? Can we, for example, find an algorithm that takes big O of n times h time if the convex hull has h vertices? Note that if h is rather small, this could be a faster algorithm. And even further, can we design an algorithm maybe that takes big O of n log h time? And the answer to both of these questions is yes, we can, and we will discuss this in the following. We're gonna design an output sensitive algorithm whose running time will depend on the size of the output. In our case, it will depend on the number of vertices that will lie on the convex hull. So the idea that we're gonna use here is we're gonna find the first point that definitely lies on the convex hull, And then we're going to try to wrap around the remaining points while building the convex hull. So let me propose the following pseudocode, and in the right bottom corner, I'm going to illustrate this with a small example. So first, we start with a virtual point somewhere at infinity p0, and we find the rightmost point p1 from the input set p. And we insert p1 into the list L representing the output of the algorithm. Next, we will execute the while loop that does the following. For the next point pi plus 1, we want to choose such a point that maximizes the angle pi minus 1, pi plus. So for the first step, we want to find point p2 that maximizes the angle p0, p1, p2. So in the first iteration of the while loop, our algorithm will consider all the points from the input set P, find the one that maximizes the angle, and place this point into list L. In the next iteration, we are looking for the next point that maximizes the angle P1, P2, P3, and so on. In this way, we are wrapping around our input points, and at the end, once we reach the first point, we break the loop and return the list L. To prove the correctness of the algorithm, we can use the loop invariant of the following form. Points P1 through Pi are the first I points of the convex hull of the input set of points. To prove this invariant, we start with initialization. Indeed, P1 by construction is on the convex hull. And in the maintenance, we can use the property that the algorithm ensures that all the points lie to one side of a line drawn through Pi and Pi plus 1. So now let's again analyze the efficiency of the new algorithm. The first line will take linear time because we are finding a vertex with a maximum x coordinate. Line 3, for the same reason, also takes a linear time to execute. And lines 4 and 6 both take constant time. Finally, the while loop will execute h times, where h is the number of vertices on the convex hull. So to put this all together, the total running time adds up to big O of h times n. So now we have designed two algorithms, one that takes n log n time to execute and another that takes n times h time to execute. The question is, when do we choose which algorithm to use? And of course, the answer is when we know that the convex hull has few points on it, then we're going to use the second algorithm. And if the convex hull may contain a lot of points, then we're going to use the first one. Again, I'm going to ask the question, can we do better? And again, the answer is yes. We're going to use a trick that combines both of these algorithms in a very smart way and achieves a better running time. Before I show you the last algorithm for today, let me introduce you to Timothy Chan. He is a computational geometer, and if you ever attend one of our computational geometry conferences, you may see him there. So let me keep him here in the corner, and I'll tell you about the trick that he has invented that allowed him to speed up not only the convex hull algorithm, but also many others. So what Timothy suggests is the following. He says, suppose that we know h, suppose that we know the number of points that will lie on the convex hull. Then we can do the following trick. First, we start by partitioning the input set of points into smaller sets pi with h points each. Then within each of these sets, we can run the gram scan algorithm. And finally, to merge all the resulting convex hulls, we're gonna use a gift wrapping technique. So the first part is applying gram scan n over h times. And the second part is using the gift wrapping algorithm to construct the final convex hull. So let's look a bit closer at what the gift wrapping part of the pseudocode does. Again, we start with P0 at infinity and P1 being the rightmost point in the set P. And then we repeat the following operation h times. We have the nested for loop that goes over all subsets Pi, and within each subset, it finds the point that maximizes the angle Pj minus 1, Pj Qi. Finally, in line 8, out of all these maximum points within each set, it finds the global maximum point that will be added to the list. So now let's quickly analyze the running time of this algorithm. And this will be easy because we know the running time that each component will take. So we know that line 3 will take big O of h log h each time it executes. And the total number of times that this line will execute is n over h times, because that's the number of subsets that we partition P into. So the total running time of this part is big O of n log h. For the second part, the trick here is to find point Qi in line 7 in the time that is logarithmic in h. Trust me for now that this is possible. I'll show you in a moment how this can be done. Finally, the lines 8 and 9 take the following time to execute. We have two nested loops which result in lines 8 and 9 executing h times, and line 7 executing order n times, and this is because the outer loop executes h times and the inner loop executes n over h times. So if we put these together, we can see that the second part of the algorithm also takes big O of n log h time. So this is going to be the total running time of the algorithm, big O of n log h. Now let's see an example of how this works. We start with 16 points. We split these points into 4 subsets of size 4. And for each, we run gram scan to compute their convex hull. So now we have 4 smaller convex hulls that we want to merge into one big convex hull. We start with a point P0 at infinity, and now within each convex hull of the subset, we find a point that maximizes the angle to the already constructed chain. The reason why this can be done in logarithmic time in h is because the points of each convex hull are ordered in the counterclockwise order around the polygon, which allows us to find tangent lines from any point in logarithmic time. So now, after we have completed the gift wrapping part on the convex hulls built in the previous part, we are done. Okay, but we did make an assumption that we know the value of h. What if we don't know the value of h? Here I'm gonna show you again the same pseudocode as before, but I replaced h with some parameter m here. So now let me hide the running time analysis, and I'm gonna add 2 more lines before the end of this algorithm. What this will do is, if m is large enough that we will finish wrapping our convex hull and end up closing it up in the loop, then we return the list L successfully, and otherwise we return a failure. So now we can call on this algorithm for multiple values of m, and hopefully we will end up with a reasonable running time algorithm that will be a function of t, and we will call the previous algorithm for that value of m. So now I want you to pause the video and think of which function for m you would suggest and which running time this function would result in. And the answer here is that m should take the following function. It will be the minimum between n and the 2 to the power of 2 to the t. The idea here is that m will grow fast enough so that we will hit the correct value for the convex hull quick, but it doesn't grow too fast that we don't waste too much running time. So let's analyze the running time of this algorithm for this choice of m. Well, the main procedure in line 3 takes n log m time, which in our case will be big O of n log of 2 to the 2 to the t. Now, how many times this line will get executed? Well, we will terminate when we reach h. So the value of t when we break out of this loop will be log h, and thus this line will get executed big O of log h times. So now putting the running time together, we get that the total running time will be given by a sum for t from 0 to log h of big O of n of log 2 to the 2 to the t. Log of 2 to the 2 to the t is just 2 to the t, right? And now we can replace the sum using the formula for the sum of the series of exponents, which reduces to the total running time of big O of n log h. To summarize this unit, we have started with a naive simple algorithm that was pretty slow but straightforward to come up with. Then we developed a more efficient algorithm called GrandScan. We continued with an output-sensitive gift wrapping algorithm, and finally we used Timothy Chan's technique to join the two algorithms in one and obtain a better running time. There are other techniques to compute convex hull that we haven't covered. A natural approach to take here is to consider a divide and conquer approach, where we recursively partition the input set of points into two subsets, solve the problem on each subset, and then merge the solution. Depending on how we partition the input set of points into two subsets, we can encounter different challenges. For example, if we arbitrarily split the points into two parts, like you can see in the image, then to merge the two solutions, we will need to find extreme vertices in each direction. We could partition the points, for example, using their x coordinate. So find the median x value. Everything with the smaller x coordinate is in one subset, and everything with the larger x coordinate in the other subset. To merge the solutions to these two subproblems, we would then need to find common tangent lines. Finally, let me say a couple of words about convex hulls in higher dimensions. A convex hull of a point set in 3 dimensions is a convex polyhedron. It will have vertices, the 0-dimensional objects, edges, the 1-dimensional objects, and faces, which are the 2-dimensional objects. The interior is going to be the 3-dimensional object. The boundary of such a convex hull can be represented as a planar graph, so it will have linear number of vertices, edges, and faces. But if we go into higher dimensions, which of course is possible, our convex hull in, for example, 4D will have vertices, 0-dimensional objects, edges, 2 facets, and 3 facets, and the interior will be a 4-dimensional object. Now, the boundary of a 4-dimensional convex hull can have quadratic number of facets in the worst case.